Actually, you gotta do a talk or building, and it reads your academic track. Like actually,
I use that. I use this one. You get a constant curve. I think I haven't studied for a while. I was waiting for 10 minutes after every class. Just like a few. No, now I know it's after good afternoon, everyone. Good afternoon. So today we have our very own Dr. Mohamed Zaki, who joined us in June last year, 2022. And he's today going to give us a very cool talk about his work on intelligent transportation systems. I'd just like to make a note that for those in the back, you may not think we can hear you, but we can hear you at the front whispering. So please refrain. The acoustics of the room are such that noise carries downwards. Okay? So please avoid whispering. We can have a discussion at the end. So please.
So hi everyone, thank you for giving me the opportunity. I'll talk about something today that was supposed to be part of my course, and I decided that okay, I better spend my class on something else. Not necessarily because it's not important, but because of scoping. But maybe many of you already attending my class, so that's in addition, it's a bonus class for you. Right? And I will give solution. I will talk, of course, in the question here about how active mobility can navigate shared facilities. I will talk about what does it mean active mobility, what are shared facilities, and so on. But also, I'll talk about the future. How to think when we talk about those shared facilities that are where people walk, people bike, skateboarding, use skateboards, but also there will be autonomous vehicles there, right? So we're expecting autonomous vehicles to be on the road in the next 10 years. Maybe some of you already been in the autonomous vehicle. No, anybody? No, not yet. Anybody get hit by autonomous vehicle before? I did. You too. Okay, so they are not smart, right? It's just Silicon Valley tried to pretend they're smart. It's not. Anyway, so we'll talk about the challenges. I'm not giving a solution how to design autonomous vehicle, but I'm talking about the things that you need to think about. And transportation engineers and computer engineers and engineering in general, when we have a road shared between pedestrians, cyclists, as well as autonomous vehicles. Okay. Okay, so I'm motivated by this article that was in IEEE Spectrum a few years ago, and I like the image a lot. And actually summarize lots of things that will be happening and start having around. So who doesn't like their phone? Nobody, right? Who should walk while look at their phone? Nobody? Me? Please don't do it. But again, so we are this actually. So and in the future we have also these gadgets, like you have different way of moving, and we will have autonomous vehicles, and inside the autonomous vehicle as well. When you talk about autonomous vehicle, we have cars, but we have people that might act as drivers sometimes if it's not full autonomous. But again, they're distracted as well, right? So the question is, okay, how to navigate that? Right? We're building as researcher, we build for the future, not for now. Okay. So I always come back, and actually I thought about making the talk, the title, will overly polite self-driving car brakes for journey, and then say, okay, maybe it's not a good idea because I typically spectrum consumer, right? So, anyways, in reality, that's what we have, something very close. And this is the real project I was working on. And people in my class probably saw this. You see, so we have this self-absorbed person, whatever is the reason. There might be more to the story, but we're lucky enough it was not hit, right? First, there are a few things you need to observe. This intersect, there is no crosswalk. This cycle shouldn't actually cross from here. It's not green for the cyclist to cross, right? But luckily the vehicle, here's the driver without window. But can you imagine the driver was watching YouTube or chatting or texting? That would have been different outcome, right? What you see is the trajectory. I'm putting there just kind of tracking the behavior, and that's what we're trying to aim to. I will talk a little bit about this, how we can measure these interactions. I'll be high level, so I'm not going to lower level explanation, so don't worry about it. Okay, but coming back to reality, those are a few years back. It was a summer in Toronto, maybe 3-4 years back. You have this same period, you have this kind of news that people get struck down over and over again. And it's Toronto, of course, we can say, oh, London is not Toronto, right? That's what we like to say, but still we have the same issues, and London is growing and people are moving from Toronto and other bigger areas. So we have those challenges that we need to think about, right? So not only the future, but also the current condition. We cannot, if you don't look also what's happening now, to be equivalent. So what is the objective? So the objective is to reduce fatalities and to improve sustainability. I don't know if Congo exists, but I'm from Cairo and we have similar problem. I guess you can see similar, you can connect, many of you can connect if you're coming from other places to this type of traffic. So it's not good for sustainability. Many of you are studying sustainability from different perspectives. And do you know what white bicycle is? Anybody have a clue?
Someone was killed.
Yes, someone. So usually when someone unfortunately gets hit by a cyclist, by a car or for any other reason, they take the bicycle, paint it white and put it in the location as a reminder of what's happening. I hope we will not have something like that here in London, but I was in Washington, DC, walking in downtown and just saw one. yeah, it's heartbreaking when you see the reality. So, and in general, you see it's 1.3 million people all over the world, right? So when we think about transportation, we cannot think only about, oh, Canada, we have better transportation. We think about all the world to solve those problems, okay? So we have to think globally. Another happened 2011. This, I recall quite well this news. So there is this intersection. There is facility, like kind of road on in Atlanta, Georgia, and there is this mother is just going to the bus stop, and there is around 1 kilometer between crosswalks, both sides, or half a kilometer, something like that. So the mother has to cross to the bus stop. You see here the bus stop, and the kid got killed, and she was convicted because, oh, she's responsible for the well-being of her kid. Is it true? You know, I mean, it's unbelievable that she should have taken the precautions. She shouldn't have jaywalked. She should have walked 1 kilometer or to take and then return another kilometer to the bus stop, right? Fortunately, I didn't know that, but I was Googling today, and actually she was only get again a jaywalking ticket at the end, but it took 2 years in jail to do that. So basically, that's another bad news for pedestrians. Like, if you think about sustainability and health of the society, it's not a good thing. So, okay, and that was 10 years ago. I don't think it changed, and I'm aware. I was in Florida, and some people told me there are similar situations happening on the east coast of Florida. Exactly the same conditions. People get hit because they cannot cross, and usually they are in communities that are less privileged, where the infrastructure is improvement are not something of a priority. So there are lots of probably political decisions involved. Moving to the future again. So do you recall? Anybody recall this image? Okay, so Uber. Few years back, they have an autonomous vehicle division, and they were doing, and they still have it. They still have this division, but through a subsidy, another company. So they don't take responsibilities anymore of more data, basically doing research. That's what I knew from someone working there. Yeah, that's what I understood. So basically, this guy was the driver, just sitting watching the street. Like, this is autonomous vehicle, and I guess he was distracted, and the car hit this pedestrian, and this pedestrian basically, they're walking with their cyclist next to them. So the autonomous vehicle didn't recognize what this shape. They can recognize the pedestrian, they can recognize the cyclist, but not a cyclist next to a pedestrian. That's machine learning at the best, right? Stupid still. So of course, this is the impression of the guy. I guess there's a video. I didn't see the whole video. I couldn't watch it. But sadly, this person died. And some say, okay, this is the price for technology, right? If we don't experiment, we will not have technologies, right? But so that's the reason. So, and then after the investigation, so the transportation board, they say, of course, victim blaming. The victim was on meth, which type of drugs, popular and for lots of disadvantaged people. And this led her to jaywalk. Again, jaywalk. So they tried to start by, okay, her fault. She jaywalked. And then, but on the other hand, okay, our machines are not properly programmed. So they acknowledge the computer inside this Uber car didn't recognize a pedestrian outside of the crossing zone, which is problematic a little bit. I mean, you expect the car to be recognizing, if you want to self-driving car, this car has to recognize things around it, right? Not only on crosswalks. Otherwise, if you drive in India or Cairo, you know, it will hit everyone, right? So anyway, again, you can Google all this information. It's not my invention, but it's kind of weird, right? It's non-engineering logic kind of. So what to consider basically? There are many things to consider, but there are two things that are very important to consider. I'll talk in our talk today. I don't think I have time to talk about the second part, but I'll talk about a little bit on the first part, what we need to think about if we would like to avoid the safety concerns, okay? I'm not talking about the social element. We touch a little bit, but I'm talking about the engine from transportation perspective. So we need to analyze and understand road user behavior, right? Whether you're a pedestrian, you're a cyclist, whether you're in the car, level 3, for example, distracted, how are we gonna communicate, right? And also, on the other hand, we need to make sure that whenever we design this computing solution, the technologies, we have to make sure they are adhering to specification and they're well designed. I mean, well designed, well tested. And the aspect, I was talking to someone here in the university on AI ethics in philosophy department. So it's a big thing. Think about if you're going to develop AI systems, how to incorporate ethics in it. So which is beyond my knowledge, but it's important. As you see, when AI make decisions, sometimes they can be biased, and we need to remove this bias somehow or reduce this bias. Okay, but in general, and working, so this give us to the concept of road safety. What can we do, basically? So as engineers, as civil engineering, even though I'm not by training civil engineering, I'm here in the civil engineering department, so I have to think like civil engineers. So so we look at road safety. We cannot look at the car much here because this is the other engineers that look at this problem, but we can look at road infrastructure and how we use the built infrastructure, how we use it, okay? So we can look at what causing these problems. If we find a solution, let's say we find that there are lots of conflicts or crashes between pedestrian and cyclists, for example, we can separate them into separate lanes, right? Many places now they're separating even pedestrian and cyclists, right? And even scooters now is a problematic. We bring a scooter to campus, right? I guess, or at least to London soon, or at least there's a decision on that, like the sharing scooter. And the question, where we can drive them, okay? Can we drive them in bike lanes or not? Some people say yes, some people say no, depend on it. Can we drive on a sidewalk or not? So we have to understand the effect. If we decide on certain treatment or certain design, what's the impact of this treatment? And what's the alternative? So, okay, if solution one doesn't work, what is the other solution? Of course, there is the cost, there is politics involved, and all the other things. But as an engineer, we have to think still about those things. And we move to more radical questions. Can we stop collision at all? Can we have what you see zero collision, zero deaths on the road? Some people say it's possible, and I don't know if you heard about Vision Zero. Vision Zero is a concept. I'm not talking about it here, but in summary, it's a concept that was developed in Sweden in the 90s, and actually is part, each government has to implement Vision Zero in their policies. So every new government that's sworn in, part of their agenda is how to implement Vision Zero, and basically it's how to improve the roads, so there are no collisions. And that's why Sweden, I haven't been, but I heard this is one of the best places for people to walk and one of the safest in the world to drive. And to do that, we have to think about more proactive methods. Think about how to prevent actually crashes from happening at first place, okay? Again, I'm not talking about the road safety. If you like that, maybe next year I register my class. So I'll talk in detail about road safety. But here I'm telling you that using those methods, what can you do? Okay? It's more like case studies. Okay, so I'm interested in computer vision a little bit. And I think computer vision from infrastructure, because we have them on next to a camera pole, a traffic pole, and so on, we can get lots of things happening. And you don't have to try to figure out what's going on. But that's the intersection in China, and you see there are lots of traffic there. The pedestrian, trucks, buses, bikes, and we find e-bikes as well. And they're all using the road everywhere, okay? And you start to think about that, okay, that's confusing. Okay, we try to make sense of that, okay? I'm not trying to give a solution here. I'm trying to give you that the extent of the problem can be just by zooming in on one simple interface. But how to do that? There are now many technologies available. I have my students now that can build a computer vision system in like 1 week. It took us 10 years to build this before. And I was the second postdoc. So that's not my work, that's work as a team. But now with machine learning advances, that's kind of prehistorical method. But what we're trying to do basically, so to make it easy for you to understand, we're trying to identify different features of moving objects and try to group them together to make sense of what this object is. And at the end, we try to measure things like the speed of those objects, or now we identify them and classify as pedestrian, cyclist, car, and so on, of course. And then we try to get measures of their speed, the location, using what kind of mapping between real coordinates and the video coordinates. And from there, we can measure how close those interactions between the vehicle and the cars, and we get measure of safety. So if we can quantify these interactions and how they are severe, we can come up with a mapping of where the problems are happening because we know the location, how severe they are happening, and what are the road users involved in that, okay? So at the end, after all the struggle, many people involved, buggy software that we having, we get this. So what we have here is the map that shows basically what are the severe conflicts. For example, here we interest pedestrians, and then we can pinpoint definitely the corner where there is right turns and so on. So we can have some kind of mapping showing where problems are happening, which is good, right? So at the end, we need something to help us visualize where the problem. We can get information about the distribution, we can get temporal distribution, and so forth. You can do a lot once you get this data, right? So that's the aim. So first, as engineers, we need to map to identify the problem, remember? Once we pinpoint where the problem, maybe we can find a solution here, for example, to make a vehicle come to a stop or no right turn or red, for example. That's a simple solution, right? It just needs some will to do that, but we have to identify the problem first. But here I'm not talking about mainly road safety. I would like to go beyond this interaction. I would like to step back and look at try to understand how pedestrians are walking. And if we have time, which I don't think so, we talk about bikes a little bit, cyclists. So the difference between pedestrian and cars, pedestrian can walk anywhere, right? I mean, some cars do, but not to the extent. They're still limited by the roadways, right? Still, sometimes they do some crazy stuff, but we can assume they are well-behaved than pedestrians. And pedestrians also, their way of walking will be different, depending on if they're distracted, if they're talking to their friends while crossing the road. If you have kids, the elder people walking with them, around school zones, around hospitals, all that. So it makes things different. So we need to understand that. So we need to understand what are the attributes, and we need to see how they react when they are in a kind of critical or dangerous situation, what type of actions they take. And we need to do that in a kind of automated manner, because if you have many pedestrians and we try to do it manually, it's difficult, right? That's why the computer vision was happening. But assuming now we have the trajectories from this computer vision, so I'll look at 3 levels of understanding. Hopefully will let us understand how people walk. So the first one is through what we call operational. So how people walk, how many steps they take per second, what's the length of their step, and what the average speed. So it can tell us a lot. If you try to catch a bus, you will run. But if you're trying to walk as an elderly and a young adult, probably young adult will adjust their steps and the step length to accommodate the elderly, right? You don't leave your grandpa and walk, right? So this is important when we design facilities. And also when we design, when we hopefully feed the computer vision and other sensor of the car so they can take a more informed decision, right? If they understand those are elderly people I have to be more careful, especially when in the future there need to be some sort of a communication mechanism between the cars and those pedestrians, right? So I will skim through every one of those elements and talk briefly about what we did there, okay? So when we zoom in on the way people walk, the walking mechanism is like, we don't roll, right? We just walk one step. So you see, right? Every time you put your heel on the floor, so it's just one click, two clicks, one click, right? So it's kind of size, it's like a clock, really, except it's not, it varies, right? So it's kind of sinusoidal. And that's revealed a lot about, if you start taking this measurement, if you can collect this and we can do it using computer vision, we can have, and this is totally automated. Then we can apply some sort of analysis, which I guess many of you know, frequency analysis. Then we can get a dominant frequency, which shows that the dominant step frequency, which how many steps you take per second in our case, okay? And if we get that, and then we can have labeling, let's say, attribute between based on gender, age, and so on, we can figure out that during certain behavior, for example, a male will take longer step lengths versus a female will take more increase the step frequency to deal with situation. And that's what we've been looking at. Of course, our research is also based on what medical science and other domains have been looking at. But in our case, we're focusing on the transportation elements, and this is very important because we can see how they react in different situations. Okay. Again, when you have after filtering and so you get the smooth trajectory, and of course here it's not perfect, right? Because as a person walks, so you have to navigate other people, and then the speed is not accurate. In general, we can get the average speed across a certain location. Okay. And of course, when you do research, you have to make sure it's correct, right? So we have to do validation, and we have to make sure, and we have very kind undergraduate researcher and grad researchers spent hours and hours going frame by frame over videos, trying to do this manually, which is, I remember, yeah, good students, great students. I'm sure you are too. So, but we have to validate this equation, which say the steps, the walking speed is a relation between the step frequency and the step lengths. Okay, if you multiply step lengths by step frequency, you get the speed. Okay, instantaneous speed of the walking. Okay, so why this is good? So here is the Chinatown in Auckland. Very nice place. So we have the data set provided there, and we look at an intersection that turned into what we call scrambling phase. So when you have a touristic place, people tend to jaywalk a lot. And when you have a large intersection, which not many in the US, they like their intersection to be wider a little bit, sometimes it's very difficult to just cross, wait, and cross again. People are impatient, right? You have to go, probably, if you have a chance, you walk diagonally. So there came some ingenious thing that, okay, we will have this what we call scrambling phase, where basically there is a phase where there are no cars driving through and people can walk everywhere. So that's called scrambling phase. It's implemented in a few places, maybe in Toronto. I don't know if there is scrambling phase. I don't know if there is scrambling phase here. I know there is one in a place called Steveston, which is south in Vancouver. They implemented one. They think about one in downtown. I don't know. So you find most people prefer to walk diagonally, most of the case, unless you go, of course, need to go to the left side. But what happened when you're in the middle and the do not walk start flashing, you know? Okay, we wanted to see how people will react under certain conditions when they cross normally on the conventional crosswalk diagonally, and also during the walking phase, like the green phase for pedestrian, and flashing do not walk, which is the yellow line. Hurry up because because it will turn red on you. Okay, so we looked at that, and then we start measuring to see how people will use their gait step length and step frequency. And for example, we can see here that always when people walk diagonally, they have to adjust the step lengths and step frequencies to catch up. Otherwise, it will be very difficult for them to catch up. Okay, and actually we did that, and then we have others who help us manually label people as best as they can. So if we are sure that male versus female, the elderly versus young, and of course you can see the difference as well. And here is not the place. If you need any of those published work, we can give you details. But the point is not to go over results here. Okay, they'll give you an idea of what we can do. Okay. Another thing we said, okay, now it's good. What about distraction? And we look at, can we identify if someone is distracted from this variation of the walking behavior? I guess if you try, don't try this, but maybe at home, try to look at something and try to walk in a straight line. You're not able to walk right in a straight line, right? Because what's happening is our brain cannot actually multitask. We think we can do that. You can be on Instagram, Facebook, Twitter, LinkedIn, and doing your homework, right? Same time, right? You cannot do that. So basically, we can do only one thing at a time. That's how we're designed. And when we distracted, so the processing, our computer can decide to put resources somewhere, and then probably it's more important to read than to control our walking mechanism. And when we don't control it, it goes out of balance and it goes sideways. So we try to detect this actually. So we try to identify people who are distracted versus distracted and see how this fluctuation changes. So the variations, those fluctuations. And of course, we have to look at free flow traffic, not because people are obstructing or something, to see if we can capture this fluctuation in the behavior. So I skipped it. So we have this person walking, and then we can identify she's distracted, typing. And then we look at we start looking, okay, how can we measure that? And talk to people in medical science or health science, and then they pointed us to some literature on the subject. So start saying, okay, how can we implement this in our tool? So for example, we can see the variability. Remember the step length and step frequency. We can see the ratios, is it stable or not? And we look at the way a human can accelerate actually, is it stable or not? We looked at these measures and many others to see which one can we capture accurately and which one is very difficult to capture. And we use them to identify whether a pedestrian is really distracted or not. Yeah. So, and we wanted to apply this. So we said, okay, what can we do with that? So we, Kamloops is a city in the desert, east of 4 hours from Vancouver. They have the Thompson River University, it's a college there, university. And it's a good place because around universities, people are distracted, right? So we're working with the government there and decided to put our cameras in a way that's not invasive, in the sense that nobody will notice them. They're just traffic cameras. So that's the idea. And we try to capture them, either distracted or not distracted. And also we can capture the vehicles coming to do right turn, right? So we can capture actually the time, the period where there are potential interactions with cars, and to see what is the behavior of distracted people versus non-distracted people. So if you're gonna get hit by a car, what would you do? Of course, we wanted to do safe, like right to the kind of safe way to look at these things. And we didn't tell them to do anything. We just basically put the camera and we stayed in the hotel for 2 days, basically, to get the data. Yeah. So, and we have some observations. So first, when you're distracted, you have a problem maintaining a walking speed. You're not stable in walking. But also people who are texting and reading have more issues, right? Because your visual field is not there. You cannot sense what's around you to control your walking mechanism. So definitely, if you're texting, it's worse in terms of stability compared to when you're only talking or listening. We cannot, of course, identify if you're reading or texting. That would be difficult for us because when we work with government, privacy is important. We cannot capture faces and so we have to be a little bit far. The camera has to be a little bit far, so we cannot capture information like license plate and faces. So we build again some information. Oh, there is a slide missing where there is basically summary of or lesson learned, but basically people when they are distracting, they tend to control most likely the step frequency. Like you crossing and you're reading. So it's very difficult for you to control your step length, but you control step frequency. You try to walk a little bit slowly to be able to account for any things you're not really can see, right? Like if there is a pothole or something. So it's come naturally that you reduce your step frequency, and we can look at that and we can capture this kind of information. I guess I missed some slide where there is information about summary. I don't remember, this was 24 years ago, but we can find this differences between texting and talking, and when there is interaction with vehicle and non-interaction. And what you see, I remember, is that a person who are full aware of their environment, when there is a car coming, they will control the step length and step frequency and their speed. Compared to someone who's not paying attention, they probably control the step frequency and nothing else, which is put them in disadvantage during decision making because they're not aware of their environment. Any question? Okay. Do you still have time?
Oh, 5-10 minutes.
Okay, sure. So the other thing I look at, okay, so that's the operational part. The operational part is like how people control their walking behavior at the very microscopic level. So we can go up and see more like decision making, like decision to jaywalk, evasive action, maneuvering, and all that. And then at the end, we see that the strategic on the longer term navigation and group behavior. So we have this, again, we work on one of the intersections that are very challenging. I'll talk more about it later on in Vancouver as well. So we have this kind of first case, someone cannot take a decision. But second case, you see here, car is moving, pedestrian doesn't care. So there is kind of what we call like indifference to the safety issue, right? But there is a reason for this location, which is Vancouver. But it gets us to ask questions. Is perception of safety the same across different locations or not? In the sense that if I'm going to cross the road here and I'm going to cross in New York and in Cairo or China, and I see car coming, will I react in the same way or not? Of course, there are many factors, but what we can look at is how I'm going to react in terms of evasive action for situations that are more or less safe. And let's see. And also the important question we wanted to ask, okay, if I'm going to use our measures here that we use in Europe and in Canada, like this, what we call time to collision, and also measures that are adapted here, are they transferable if we use them in other places or not? So again, going back to this intersection, you see this person. So this person is walking, notice there is a car, slow down, and then walk, right? Which is basically normal behavior to avoid this car, right? So it has two cars in a row. But I know, okay, the question, how can we detect this variation? And that was a challenge. Some people say, okay, we can take the sliding windows, but sliding windows didn't give us the onset of those changes. So we have to develop this kind of new indicators that capture what we call evasive action, which is the evasive action or the action made by the road users, in case pedestrian, to avoid those dangerous situations. So we use some kind of measure, we developed it, we adapted from from I guess health science again, that it used basic to change to detect brain changes in brain activities. And we figure out that we can use similar, and then they have the same characteristic as what we have when people start changing suddenly their behavior. And we saw that we looked at it, yeah, we can detect the onset. Like again, is this person, we can detect all these changes, subtle changes of stop and go and sudden change. So we didn't want to detect how fast, or we didn't want to detect the sudden changes that we cannot detect using other methods. So this pedestrian was aware of the problem. But if you look at another pedestrian here, this pedestrian is crossing and the car is coming and it's indifferent, right? So the perception of safety of this person is different than the first person. But this is, the question is, what can the perception of safety tell us about the indicator, safety indicators that we can use to assess safety? So what we did, we worked with the city here. We worked a lot with the city of Vancouver. So we have 2 engineers, and we give them this video of in this China data set where people are just crossing, and then there is a car coming, and we ask them, okay, can you evaluate the severity of those interactions? And what else we did independently, we calculated measures, what we call post-encroachment and time to collision, which are, those are measures used by engineers to estimate safety. And we have our own indicator as well. So what we have here, we don't have to try to understand in detail, but I can, again, if you mail me, I'll provide you with the paper. There was no difference from evasive to non-evasive action if you use those measures. And this is based on the confirmation of the 2 experts. So basically, those measures, they don't capture the evasive action. So they don't tell a lot about the perception of safety the different road user or pedestrian had when they are in conflict, compared to something like this entropy-based method, which captures that this sudden changes in the behavior, which shows that this person reacted to those kind of conflicts. So they were aware. So they have this perception of safety difference. So if there is no evasive action, then we don't have. So there is no change in this measure we have. But if there is evasive action, you can see this captured. And the experts agreed on that, because the experts, they look at what we looked at basically. Oh, this looks dangerous because this pedestrian was aware. So the way they evaluated the situation was similar to the way this pedestrian would have reacted basically. So that shows that basically even the methods of safety, they are not static. In Canada, we have 500,000 immigrants every year, right? They come with habits, they come with perception of safety. So if we build our roads based on the 40s or earlier, maybe 100 years ago, it won't give us the safety that we're seeking. So we need even to adapt to some sort of safety tool that help us build the road in a safer manner. You see here? So it's not only for China or Cairo or New Delhi, but also as well as here in London. Okay. Okay, I'll be fast. So if you used to Google Vancouver voltage intersection, you'll find East Hastings and Maine. Anybody been to Vancouver? Except you live there, you're born there. But if you go to Vancouver, there's, of course, or you see picture of Vancouver, there are these nice mountains, which is beautiful. But if you just go outside of downtown, it's totally different thing, right? I don't think I've been to any place that's similar to East Hastings and Maine. It's a sad place in the sense that there are lots of challenges and lots of problems that need to be solved. It's not a place to avoid. It's a place actually to try to think about, let us think about where we're going in terms of engineers. If we cannot solve these problems, did we fail as engineers or not? So it's kind of challenging. Of course, there are more problems than engineering can solve, but also maybe we have a solution for that. And I was lucky actually to be involved with the city of Vancouver to try to get some solution there and work on the safety. So, and by the way, when I used to live in Vancouver, I lived 2 blocks from here, very safe. Don't need to leave anywhere. Okay? It's not safe. So it's just challenging things. So we look at violations. We look at when people take to jaywalk. We look at the behavior jaywalking. And we look at, so we try to capture the jaywalking movement around, using kind of pattern matching and so on. And we looked at also traffic signaling and when people start jaywalking and so on. We captured that. We need to gather this information. And those are cameras from the city, not our cameras. It's very, we didn't want to, but because we knew that if we install cameras that we cause problems, so we relied on very low quality cameras that are used to be in the city back then. So, of course, some reason you need to jaywalk because traffic is horrible there as well, right? Not that pre-COVID. After COVID, I think things are easier. To start to look at different locations, very difficult to try to scan the safety across this intersection. And you can see that things make sense. So we have people jaywalking sometimes to catch the bus. And this is the same thing. So we have bus stop here and people start jaywalking, they start crossing. And any vehicle coming here and right turn, they don't see the pedestrian, then this is where the problem is happening. So we have actually one of the recommendations, why don't you find another way to place those bus stations, because to avoid this kind of jaywalking. So, and then at the end, we came a recommendation that basically installing mid-block intersection at some location where there are a lot of challenges that can help. And they installed the intersection, they installed actually the mid-block intersection. Of course, we cannot take credit. It's a work for everybody involved. But I'm happy to be part of this kind of thing. So you see some engineering thing can make impact a little bit. And one thing. So to wrap up, the strategic one, we didn't have time to talk about it, but strategic one, you look at how people walk in group, try to understand if a mother and a kid together versus friends, how we react in safety situations. So again, we try to figure out similarities in the way they walk. People tend to synchronize their walking. But if you walk with your grandpa or grandma, you try to walk at the same space, same speed. So you adjust your step length, step frequency. So in total, you have kind of similar behavior. We try to capture that. So we can identify people actually walking together, close to each other, if they're together or not, as well. And we start looking at the way they react when their vehicles are coming. So, and we see that some people, based on what we call the strength of their relationship, in terms of adjusting walking, with their split, like in this case, I guess it was a teenager and their mom, and the teenager run and left their mom to face the car, like a typical teenager, versus a situation there where they stick together. That's a tool. It's really outdated, but I guess after I left, I started a company out of it. I'm not involved, but this company, then actually I was talking to the City of London and it turned out to be one of their customers. But yeah, research is open, right? So, but I'm happy that this work has implementation, and even without seeing it, some cities like, and sometimes it's not fancy. So this is what we had sometimes to work to get cameras. So it's an roundabout in a QBC. So we have to go on top of the building, have some drum kits with some weights to put the cameras. So we can put these cameras, because sometimes you cannot install the cameras. So those are the vaccines. Those are the fun thing about engineering, right? So we have someone who's a drummer and he came up with the idea, okay, I have drum kits. So we try to improvise, but it was approved. It wasn't like, I mean, it's cool to do it without approval too, but we have this university work with us on that. So no, that was work with the university. But you can see we can do good stuff. I think I will stop here. Yeah, that's it.
So we have time for maybe 1 or 2 quick questions. Any burning questions from the audience? No? Okay, I have just one. some of this looks like it might overlap with behavioral economics from micro. Is there any interest in that in your field from people trying to compare sort of person to person interactions?
General spending and
Yeah.
behavior. Well, I'm sure there is overlap. I mean, at the end of the day, the tools can be used elsewhere. But looking at the economical impact on safety is important because you have this location where you have disadvantaged people. So you can look at certain behavior like the rate of violation correlated with certain spending or certain debts. Or I know in Edmonton there is a colleague, she did a thesis on correlating crashes with in crime area with crime-driven areas. So they look at speeding and all these problems that are happening, and they looked at where the crimes are, like small crimes, like car theft and all that. And there were clear. It's more than correlation. It's more like modeling, and there were more relationship. But this research I was not involved. So I don't know. I remember I read the thesis, but not more. But definitely there's. Things are related. We cannot take the engineering on its own. Otherwise, we'll have this autonomous vehicle that don't understand a bicycle from why a bicycle is next to a pedestrian. Right?
Any other questions?
Will you change anybody's mind to do transportation engineering?
Yeah, anyone wants to talk to Dr.
Not with me, anywhere. But it's cool. You see here you work. Yeah. Hey, thank you.
Thanks so much.